In this video, we will be talking about limiting reactants. So first and foremost, we'll begin with an example. So suppose you have 5 males and 3 females, and they have to pair 1-to-1. So you could automatically see that there's going to be an excess amount of males, and there's going to be if they're going to line up and dance or whatever, partner up 1-to-1, there will be a deficiency or a limiting amount of females. So if you're lining up one male to every one female, you're going to have a limiting reactant. In this case, that would be the females. And then you'll have an excess reactant, the other reactant in a chemical reaction. In this hypothetical example, it will be the males. So using this common example, we have the limiting being the females, and then the excess to be the males. So it's important to recognize that the females actually set the limit on how many partnerships or how many dances or however, whatever activity the 1-to-1 male to female ratio does. This sets the limit. So you can only have 3 partnerships. And furthermore, you're going to be left with an excess amount of 2 males who really don't have anything left to do. They're left out. So a limiting reactant problem, translating this to a chemical reaction, the limiting reactant problem sets the limit on how much product that you can make. It also tells you how much remains of the excess reactant. So a couple of important points here. Number one, a limiting reactant is a reactant. We established that reactants go to products in a chemical equation. The limiting reactant will always be a reactant. It will be to the left side of the arrow. It will never be a product. Secondly, the second important point is that if you have a limiting reactant, if A is a limiting reactant, then the second reactant, B, has to be excess, or the third reactant, C, has to be the excess. So if one is automatically established as limiting, then the other ones are automatically, by default, are going to be excess. So it sets the limit on how much product is made. We call that the theoretical yield, completely determined by stoichiometry and the balanced chemical equation, as this practice problem will illustrate. So one practice problem that we'd like to go over that sort of sets up a common theme here is shown here as an example. So a student prepares ammonium bicarbonate by this reaction. NH3 plus CO2 plus H2O goes to ammonium bicarbonate. First and foremost, you always have to do one thing in all chemistry problems, and it's especially important in limiting reactant problems, is balance. So make sure the equation is balanced, balanced, balanced. If you look downward here, skipping ahead, the reaction is already balanced, but in a problem on an exam, definitely want to balance the equation. All right, so this person uses 36.8 grams of NH3, one of our reactants, 50.3 grams of CO2, the other reactant. Water is in excess, so we don't have to worry about that being limiting. The question is, what is her actual yield of the ammonium bicarbonate? If her percent yield is 84.7%, the limiting reagent, the excess reagent, also known as limiting reactant, excess reactant, are things that we have to mention, as well as the theoretical yield, which is how much we would get of the product if this reaction were to occur with a 100% yield. Now that theoretically never happens, because if we do this reaction in an actual lab, there'll be spillover, evaporation, what have you. Things will stick to the side of the tube. You'll never get to 100%. However, what we do want to do is maximize our percent yield, and our theoretical yield is how much we could get if everything was 100% yield. All right, so the equations are given to you. The percent yield is the actual yield over the theoretical yield. Here, the actual yield is something that we will have to calculate based upon the percent yield of 84.7%. The theoretical yield is the yield that we will get from stoichiometry. So the first thing we have to do is make sure it's balanced. So they already gave us the balanced equation. The second thing we need to do is ask ourselves 2 questions. So we need to determine the limiting reagent. And the limiting reagent can either be NH3 ammonia or CO2 carbon dioxide. So we need to ask ourselves scenario 1. In scenario 1, what is the yield of ammonium bicarbonate if all of the NH3 is used up? That is to say, if the NH3 was limiting, if all of it was used up, how much of this product can we theoretically get? So let's go ahead and ask ourselves that question and use stoichiometry to answer it. So the equation is already balanced. Our first question that we want to do to set up this problem is what is the amount of product NH4 HCO3 ammonium bicarbonate that we will get if all of this NH3 reactant is used up. So we started out with 36.8 grams of NH3. Let's go ahead and convert it to moles and then use the coefficients of the balanced chemical equations to determine the relationship. The relationship is for every 1 mole of NH3, there's 1 mole of ammonium bicarbonate because the equation is balanced. So 38.6 grams of NH3, let's go ahead and convert it to moles. Using the periodic table, I got a molecular weight of about 17.04 grams of NH3 per 1 mole. Yours may be a little bit off here and there. And now let's do the mole-mole relationship based upon the coefficients of the balanced chemical equation. Like we said before, for every 1 mole of NH3, there's 1 mole of ammonium bicarbonate, so it's a 1-to-1 ratio. So let's notice how the arrangement of this conversion factor, the moles of NH3 will cancel out with the moles of NH3, and the grams of NH3 cancel out with the grams of NH3 here. And let's go ahead and convert this moles of NH4 HCO3 to grams, utilizing the molecular weight. So using the periodic table, I am getting 1 mole of ammonium bicarbonate has about 79.1 or so grams of ammonium carbonate. So yours can vary a little bit, slightly here and there. Again, the moles of ammonium bicarbonate cancels with the moles of ammonium bicarbonate. Doing this on my calculator and canceling out all my units, notice I'm getting grams of it. Actually, this should not be. So canceling out all my units, I'm getting, and putting this in my calculator, I'm getting 179.2 grams of ammonium bicarbonate are produced if all of this NH3 is used up. Okay, so that is, or potentially could be, a theoretical yield. We have our second question to ask. So here's our question number 2. We know how much is produced of the product if all of the NH3 is used up. Now we're going to ask ourselves the same thing if how much CO2 is used up. So we're starting out with 50.3 grams of CO2. Let's highlight this in green, I guess. And let's go ahead and convert it to moles. Balanced chemical equation is for every 1 mole of CO2, there's 1 mole of ammonium bicarbonate. And let's go ahead and do this stoichiometry. So converting that to moles, and then we have a 1-to-1 ratio based on the balanced chemical equation. Let's put that in. And let's go ahead and do our next step and convert the moles of NH4HCO3. Remember, all our units are going to cancel out to grams of NH4HCO3. And we know that for every 1 mole, there's about 79.1 grams. So I'll just copy and paste that. Just want to bring your attention once again to canceling out of our units. The grams of grams cancel. Moles of CO2 cancel. The moles of ammonium bicarbonate cancel with the moles of ammonium bicarbonate. And we're left with grams of ammonium bicarbonate just as we were here. And that's what we want. Doing that on our calculator. So doing that on their calculator, I'm getting 90.18 grams of ammonium bicarbonate. Let's highlight this in green and highlight the 179 grams of ammonium bicarbonate from NH3 usage. Let's highlight that in yellow. Automatically now we can determine what our limiting reactant is. The limiting reactant has to be a reactant, so it's either NH3 or CO2. It turns out it's CO2. So if all of the CO2 is used up, we're going to make 90.18 grams of ammonium bicarbonate. That's calculated based on stoichiometry. So you're going to make 90.18 grams of that, and then all of the CO2 is used up. There's no way you could get to 179.2 grams of the product. Why? Because after all the CO2 is used up, there's no more CO2 to react. What you have here left is excess NH3. So the key point here is that the CO2 sets the limit on how much you make. You're going to make 90.18, and then the reaction stops because all of this reactant CO2 is gone. So the theoretical yield is also based on stoichiometry. If we were to do this reaction perfectly, okay, like robots, exceptionally perfectly, we should get 90.18 grams. That's called the theoretical yield. We will never achieve the theoretical yield because we are, after all, humans. So the theoretical yield is 90.18 grams, and the limiting reagent here is going to be CO2. The excess reagent is NH3. So let's determine the actual yield here. So going by this equation, percent yield is actual divided by theoretical. We recognize that the theoretical yield is going to be 90.18 grams of NH4CO3. That's your theoretical yield. And it's 84.7% is the yield. So I'm going to divide that by 100 because we don't generally when we deal with percentages, it's multiplied by 100 to get the actual number. We divide by 100. So don't forget to divide this by 100. And so 0.847 and 84.7% are exactly the same thing. So solving for actual yield here, I'm getting 76.38 grams as being our actual yield. Let's highlight that. So we got our theoretical yield, which is 90.18 grams in green. Our actual yield is 76.38 grams as determined by 84.7% yield that was given to us in the problem here. Limiting reagent is CO2, our excess reagent is NH3. Now we can further extend this problem by actually calculating how much excess NH3 remains after the reaction is complete. So let's just go ahead and do that even though it's not mentioned in the problem. So remember, the key aspect of a limiting reactant is that it sets the limit on everything, not just how much product you produced, but also how much excess remains left over after the reaction goes to 100% completion. So stoichiometry will help answer that. So we start out always with our limiting. So we're asking ourselves the question, how much of the excess reactant is left over? Sort of a extension to this problem. We start with our limiting because that sets the limit of everything, 50.2 grams. Let's go ahead and convert it to moles and recognize that for every 1 mole of CO2, there's 1 mole of NH3. And let's go ahead and convert the moles of NH3 to grams of NH3, recognizing that the grams of CO2 cancel, the moles of CO2 cancel, and let's do one final conversion factor, converting the moles to grams. Doing this on my calculator, I am getting an answer of 19.42 grams of NH3. That's what's going to react with your limiting of 50.2 grams of CO2. So how much excess left over? We started off with 36.8 grams of NH3. Well, that's the excess. 19.42 grams of NH3 reacts with the CO2 before the reaction is halted because there's no more of the limiting. So how much is left over is going to be this 36.8 grams minus this 19.42 grams. So the amount of excess left over after that subtraction is 19.2 grams of your monet NH3